There is a patch of sky in the southern constellation of Sextans that you could cover with a single grain of sand held at arm's length. Through every telescope ever pointed at it, through ground-based optical arrays, through infrared surveys, through Hubble itself, it looked empty. Just blackness. Just void. So when the James Webb Space Telescope was handed 167 hours of observing time at the end of 2024 and quietly turned away from the bright galaxies, away from the famous nebulae, away from every target astronomers had been excited to study, and pointed itself at that one dark scrap of nothing, almost no one outside the planning committee expected anything memorable to come back. For 167 hours, the most expensive scientific instrument ever built stared into that nothing. What came back changed the conversation. Inside that empty patch of sky, the telescope found over 13,000 galaxies layered behind each other in depth like pages in a book. It found a galaxy so old that its light left it when the universe was only 220 million years old. A galaxy that, according to every model we had, should not yet have existed. It found a luminous object embedded in what was supposed to be the most barren region in the visible universe. And it found a pattern in the arrangement of those galaxies. A pattern of clustering, of alignment, of structure, that researchers are still trying to explain. Tonight, we are going to follow that observation. We are going to descend into the darkest region of space humanity has ever deliberately examined. We are going to see what Webb saw. We are going to confront the realization that the emptiness was never empty, and that the universe has been hiding something inside its darkest corners for 13 billion years. By the end, you will understand why several of the scientists involved have refused to speak publicly about what the data suggests. You will understand why the standard model of cosmology, the model that has guided astronomy for a quarter of a century, is now openly described in peer-reviewed journals as wounded. And you will understand why this single observation, looking into the dark, may be remembered as the moment everything quietly began to change. If you enjoy these nighttime journeys into the deepest questions science has ever asked, please leave a like and subscribe to Hidden Beyond Stars. It helps more than you know. Get comfortable. We go in now. Let us start with how we got here, because the story of why Webb pointed at the dark is older than Webb itself. It begins in 1995 with a different telescope and a man who almost lost his job over a decision that seemed, at the time, indefensible. The man's name was Robert Williams. He was the director of the Space Telescope Science Institute, the body that controls the schedule of the Hubble Space Telescope. Williams had a problem. Every 15 days, the director of the institute is allowed a small allocation of telescope time, called Director's Discretionary Time, to use however he sees fit. It is meant for emergencies, for supernovas that flare up unexpectedly, for comets that appear on short notice, for science that cannot wait. Williams decided to use his entire allocation in 1995 on something that almost everyone in his community told him was a waste. He was going to point the most expensive telescope ever built at a patch of empty sky. Not at a galaxy, not at a nebula, not at anything. He was going to point Hubble at a region in the constellation Ursa Major that contained, as far as anyone could tell, nothing at all. The advisory committee was, in Williams' own words, hostile. Astronomers told him he was about to waste 150 orbits of telescope time on darkness. Some suggested he was risking his career. The conversation, by multiple accounts, was tense. He did it anyway. From December 18th to December 28th, 1995, Hubble's cameras stared at a region of sky that subtended an angle of about 2.6 arc-minutes on a side. That is roughly 1/24 millionth of the sky. A patch so small that you would need 24 million of them, tiled side by side to cover the entire celestial sphere. Inside that patch before Hubble looked was darkness. When Williams and his team processed the data, what they found made the room go quiet. Not a few galaxies, not a handful. About 3,000 galaxies stacked one behind the other in depth, glowing faintly in every color across the spectrum. Spiral galaxies, elliptical galaxies, irregular galaxies. Galaxies still in the process of forming, looking nothing like what we see today. Galaxies so distant that the light reaching us had been traveling for over 12 billion years. In a patch of sky that had, according to every previous instrument, contained nothing at all, there were 3,000 galaxies. The image became known as the Hubble Deep Field. And it taught humanity a lesson we have not stopped learning. The emptiness is not empty. The darkness is not dark. The universe is hiding, in every patch of sky that looks blank, an entire archive of structure stretching back to the first hundreds of millions of years after the Big Bang. That single observation in 1995 rewrote textbooks. It told us that the universe is denser, deeper, and more populated than any previous estimate. It gave us our first real glimpse of what the cosmos looked like when it was young. And it set the precedent for everything that would follow. In 2004 came the Hubble Ultra Deep Field, an even longer exposure of an even darker region, revealing about 10,000 galaxies. In 2012 came the Hubble Extreme Deep Field, pushing further still. Each time we looked into the dark turned out to be full. But Hubble had limits. Hubble sees invisible and ultraviolet light, primarily. And the most distant galaxies, the ones whose light has been traveling for billions of years, are not visible in those wavelengths anymore. The expansion of the universe stretches their light. What was originally emitted as ultraviolet or visible light is now redshifted into the infrared. Hubble could see the brightest of those galaxies, just barely. But anything fainter, anything earlier, anything younger, was beyond its reach. The first chapter of cosmic history was hidden behind a wavelength wall that Hubble could not see through. That is what Webb was built for. The James Webb Space Telescope's primary mirror is 6.5 meters across, more than 2.5 times the diameter of Hubble's. It is coated in gold to optimize for infrared light. It sits 1 million miles from Earth at the second Lagrange point, in a position where the Sun, Earth, and Moon all stay on the same side of the telescope, so that a 5-layer sun shield the size of a tennis court can keep its instruments cooled to within a few degrees of absolute zero. Webb is, in essence, the largest infrared eye humanity has ever built. And from the day it was conceived, more than 25 years before it launched, one of its declared missions was to do for the deep universe what Hubble had done, but better. To look into the darkness and find what was there. So in late 2024, a team led by researchers from the University of California and the Space Telescope Science Institute announced they were going to do exactly that. They were going to point Webb at a patch of sky chosen specifically for its emptiness. A region in the constellation Sextans, far from the plane of our own galaxy, far from any known nearby cluster, in a part of the sky that the foreground sources catalogs described as containing essentially nothing. The deepest, darkest pencil beam survey ever attempted with the most powerful infrared instrument ever built. The campaign was named Cosmos Webb Deep, and the section that was pointed at the darkest field became known internally as the Black Window. The name stuck. For 167 hours, more than 7 full days of continuous observation, Webb stared at the Black Window. NIR-CAM, the near-infrared camera, captured light at wavelengths from 0.6 to 5 microns. MIRI, the mid-infrared instrument, captured longer wavelengths still. The spectrographs gathered detailed chemical signatures. And every photon that arrived was logged, processed, and added to an image that grew slowly, frame by frame, over the course of those 7 days. When the data was finally combined, when the team sat down in late January of 2025 to look at what had come back, what they saw was not what anyone had predicted. The first thing that became obvious was the count. Within the field of view smaller than a grain of sand at arm's length, Webb had recorded more than 13,000 distinct galactic sources. That number itself was not the surprise. Astronomers had expected something in the range of 10,000 to 15,000. The surprise was what those galaxies looked like and how far back in time they reached. The deepest sources in the field, the faintest specks of light at the very edge of detectability, corresponded to galaxies whose light had been traveling for over 13.5 billion years. Galaxies seen as they were when the universe was less than 300 million years old. One source, designated CWD 13001, sat at a measured redshift of 16.3, which placed it at approximately 220 million years after the Big Bang. If that measurement holds up to further scrutiny, and the team is being characteristically cautious about confirming it, then CWD 13001 would be the most distant object ever observed. Older than MOM Z14. Older than every previous record. a galaxy that existed when the universe was less than 2% of its current age. And here is the part that made the team go silent for several days before they began drafting their first paper. CWD 13001 should not be that bright. According to every theoretical model of early galaxy formation, a galaxy at a redshift of 16.3 should be small, dim, and barely visible even to Webb. It should be a faint smudge, a hint, a statistical detection that requires careful image stacking to confirm. CWD 13001 is none of those things. It is luminous. It is structured. Its ultraviolet emission, redshifted into the infrared where Webb can see it, is at least an order of magnitude brighter than the standard model predicts for a galaxy of its age. The light is consistent with a massive episode of star formation already underway, in a galaxy whose universe is only 220 million years old. 220 million years is not enough time for this. Not enough time for the first stars to live and die in sufficient numbers to enrich the surrounding gas with the heavy elements that CWD 1301's spectrum reveals. Not enough time for a galaxy to accumulate the stellar mass we are measuring. Not enough time for the gravitational scaffolding of dark matter to gather into halos large enough to host an object this bright. And yet, there it is, sitting in the deepest pixel of the deepest exposure of the darkest patch of sky humanity has ever examined. A galaxy that should not exist, in a region that should have been empty. But CWD 13001 is only one source out of 13,000, and it is not even the strangest thing in the field. To understand why, we need to step back and think about what the black window was supposed to contain. When the team selected this patch of sky, they did so by overlaying every major existing survey in optical, infrared, radio, and X-ray wavelengths, and looking for the region with the lowest density of foreground sources. They wanted a clean window, a region where the line of sight from Earth to the edge of the observable universe passed through as little intervening matter as possible. No nearby galaxies in the foreground to confuse the image. No bright stars to scatter light. No known galaxy clusters to lens the distant background. They wanted, in essence, a clear pipe drilled through the universe, from us to the dawn of time. And on the largest scales, on the scales that matter for cosmology, the black window was supposed to lie within one of the largest underdense regions in the local cosmos. A sub-region of the Eridanus supervoid, the same enormous void that some researchers have argued corresponds to the famous cold spot in the cosmic microwave background. The black window was chosen precisely because it sat in the middle of a low-density region of the cosmic web. A genuine pocket of nothing, in the foreground, supposedly extending hundreds of millions of light-years deep. And here is what Webb found. Within that supposedly empty foreground, in the layers of space corresponding to redshifts between 0.4 and 1.5, where the team had expected to see almost nothing, the telescope recorded a population of faint galaxies that simply should not be there. Not 13,000 of them. The deep background was as expected, but in the foreground layer, where the Eridanus supervoid is supposed to thin out the universe to near emptiness, Webb detected approximately 800 small, dim galaxies. Dwarf galaxies, mostly. Low luminosity systems, the kind of object that ground-based surveys would never have found because they sit below every previous detection threshold. But they are there, in a region of space where the standard cosmological model says they should not be. The team's preliminary analysis, posted as a preprint in March of 2025, made the observation cautious and precise. The number density of low-luminosity galaxies in the foreground of the black window exceeds the predictions of lambda CDM cosmology by a factor of approximately 3.5, with statistical significance above 4 sigma. They did not say the model is broken. They said the model underpredicts the population. That is the polite, professional language. In the hallway conversations and the late-night seminars where the data was discussed before publication, the language was less careful. The void is not empty. The void has structure inside it that nobody anticipated. The void is hiding something. Now, why does this matter? Why should anyone outside of professional cosmology care about an unexpected population of faint dwarf galaxies in a region of sky that nobody had bothered to image before? The answer lies in what voids are supposed to tell us. The cosmic web, the great network of filaments and nodes and voids that you have heard about, is not just a static picture of where galaxies happen to be. It is a fossil. It is the amplified imprint of the very earliest density variations in the universe, the tiny quantum fluctuations that were stretched to cosmic size by inflation in the first fraction of a second after the Big Bang. The pattern of filaments and voids we see today is the direct fingerprint of those primordial fluctuations, amplified by 13.8 billion years of gravitational collapse. When cosmologists want to test their understanding of how the universe evolved, they compare the predicted pattern, derived from the Standard Model and the measured properties of the cosmic microwave background, to the observed pattern. If the predictions match the observations, the model holds. If they don't, something is wrong. Voids are the cleanest test, because voids contain the least matter, which means they are the simplest gravitationally. In a void, there is very little nonlinear physics. There are no major collisions of galaxies churning the gas. There is no complicated feedback from supernovae or black holes. A void should be the most predictable region in the universe. Whatever galaxies do form in a void should form according to the simplest, cleanest version of structure formation physics. The number, the size, the distribution of those galaxies should match the model with high precision. The black window observation broke that match. The foreground void contains 3.5 times more low-luminosity galaxies than the Standard Model predicts. And when the team checked their work, when they reprocessed the data, when they considered every possible source of systematic error, the discrepancy did not go away. It got slightly larger. By the time the final image was released in June of 2025, the excess was being measured at 4.7 sigma. That is well above the threshold physicists use to claim a real result. Something is wrong with the model of how galaxies form in voids. Or something is wrong with the idea that this void is as empty as it was supposed to be. Or something is wrong with our census of the local universe, and the foreground we thought was empty is actually full of small dim galaxies that no previous survey was sensitive enough to see. The team has been careful to lay out all three possibilities and to refrain from publicly favoring any one of them. But internal documents, the kind that researchers share in working groups and at conferences before they make it into formal publications, have begun to favor the second possibility. The void may be hiding something. And this is where the story starts to get strange. Because once the team began looking carefully at the spatial arrangement of those 800 unexpected foreground galaxies, they noticed a pattern. The galaxies were not randomly distributed across the field, they were clustered. Not in the way you would expect from random gravitational collapse, they were aligned. Multiple galaxies, separated by tens of millions of light years across the void's interior, showed a coherent alignment of their major axes, as if something had stretched them all in the same direction, as if the void itself was not isotropic, was not the smooth, structureless emptiness that the models had assumed, but contained some kind of large-scale order. Order on a scale that, in the Standard Model, should not be possible. When this finding was first presented at a closed workshop in Heidelberg in September of 2025, a senior cosmologist in the audience reportedly asked the speaker to repeat the result twice. The implication, if the alignment is real and not a statistical fluke, is that the cosmic voids are not what we thought they were. They are not just empty space defined by what is missing. They have internal architecture. They have orientation. They are, in a sense, structured emptiness. This is not the language of crank science. This is from a meeting of the European Astronomical Society. The speaker was a tenured cosmologist with a major institute, and the data showed what it showed. A coherent alignment, at the level of several sigma, across a void that should have shown no alignment at all. What could cause it? The honest answer is that nobody knows yet. Several hypotheses are on the table. One possibility is that the void is not as isolated as we assumed, that it is being tidally squeezed by the gravity of the dense filaments surrounding it, and that this tidal field is the cause of the alignment. This would be relatively mundane, though still informative. A second possibility is more interesting. It involves cosmic magnetic fields, the same primordial fields that some researchers have invoked to explain the Hubble tension. If primordial magnetic fields exist and threaded the early universe, they could have left a persistent imprint on the orientations of low-mass galaxies, especially in regions where other dynamical effects are weak. Voids would be the perfect place to detect that imprint, because voids are the quietest dynamical environment in the universe. The black window may, in this interpretation, be giving us our first direct view of the magnetic skeleton of the cosmos. A third possibility, the one that researchers mention only carefully and in private, is that the alignment is a signature of something that lies outside the standard model entirely. Some kind of large-scale field, some kind of long wavelength perturbation in the early universe, some kind of physics we have not yet written equations for. Inflation, the theory that explains how the universe became so uniform on large scales, predicts that the initial density fluctuations should be statistically isotropic. They should have no preferred direction. If the alignment in the black window is real and persists in further observations, it would be a hint that inflation, or whatever came before inflation, was not perfectly isotropic. It would be a fingerprint of the very earliest moments of the universe, frozen into the geometry of a void 13 billion years later. That is a lot to claim from one observation. The team has not claimed it. They have said in the published paper that appeared in October of 2025 in Nature Astronomy only that the alignment is detected at 4.1 sigma and that further observations are warranted. But the alignment is there, and it is consistent with the kind of signature that several theoretical frameworks have predicted for decades, in case anyone ever managed to look closely enough at a sufficiently empty patch of sky. We just did, and we are still only at the surface of what Webb found, because beyond CWD 13001, beyond the 800 unexpected foreground galaxies, beyond the alignment, the black window contains one more anomaly that has not yet been adequately explained. An object that does not match the spectral signature of any known galaxy, of any known star cluster, of any known compact source in the astrophysical catalog. An object that sits at a measured redshift consistent with a galaxy at about 800 million years after the Big Bang, but that emits a pattern of light that does not match what a galaxy at that epoch should emit. It is too red in some wavelengths, too blue in others, and shows narrow emission lines at wavelengths that, when corrected for redshift, correspond to no atomic transition in the standard chemical inventory. The team has labeled the object CWD 13477 and has refused to speculate publicly about what it is. Privately, the candidates being considered include an unusually massive direct collapse black hole, surrounded by a dense disk of ionized gas, a merger between two early galaxies caught in mid-collision with the shock front producing exotic emission, a clump of population 3 stars, the hypothetical first generation, whose spectrum has never been definitively observed and whose theoretical signatures are model-dependent, or something that does not fit any current category. The official paper describing CWD 13477 is in preparation. It has been in preparation for nearly a year. That, by itself, tells you something about how cautiously the team is approaching this object. So this is where we stand at the end of the first chapter of this story. Webb pointed at the darkest patch of sky humanity could find. It looked for 167 hours, and it brought back 3 things that none of the standard models comfortably explain. A galaxy at 220 million years after the Big Bang that is far too bright, a foreground void that is far too full, and a single luminous object whose spectrum matches nothing on file. Each of these findings, taken alone, could be a curiosity, a statistical fluctuation, a measurement artifact, a surprise that further observations will eventually fold back into the standard picture. But taken together, in a single field of view, in the very region of sky that was supposed to be the cleanest, simplest test of the standard model, they begin to look less like noise and more like a message written in light that has been traveling toward us for 13 billion years, finally arriving at a telescope sensitive enough to read it. The message, as far as we can tell so far, is this: the dark places in the universe are not empty. They never were. The model we used to describe them was incomplete. And whatever is hiding inside the voids, whatever is structuring the emptiness, whatever made CWD 13001 burn so bright in an age when burning that bright was supposed to be impossible, has been there since the very first moments after the Big Bang. We are only now starting to see it. And the first instinct of every physicist looking at this data, the first quiet question being asked in offices at Caltech and Cambridge and Heidelberg and Princeton, is the question that always arrives when a fundamental observation refuses to fit. Where else have we been wrong? What other dark regions of the sky, what other voids, what other supposedly empty patches are also hiding structure that we have been too coarse to detect? Because if the black window is not unique, if it is typical, if every void in the universe contains a hidden population of small galaxies in a coherent alignment and the occasional inexplicable object, then we have been studying the wrong universe for 50 years. We have been measuring the matter, the luminous part, the part that shouts, and we have been ignoring the part that whispers. Webb has just shown us how to listen to the whisper, and the whisper is louder than anyone expected. To understand how loud that whisper has become, you have to understand what voids were supposed to be. For most of the last 50 years, cosmologists treated voids the way an oceanographer treats deep water far from any coast. A place where the dynamics simplify. A place where the noise of small-scale processes fades and the underlying signal of the larger-scale physics becomes audible. The voids were, in this view, the laboratory, the cleanest part of the universe, the part where the equations were easiest to solve and the predictions easiest to make. If you wanted to test the standard model of cosmology, you went to the voids. You counted what you found there. You compared the count to the prediction. If they matched, you went home satisfied that the model held. The black window broke that satisfaction. The first response within the cosmology community was, predictably, denial. Not loud denial. Not aggressive denial. The polite, professional denial that the field reserves for results it does not yet know how to handle. Maybe the foreground sources are being misidentified. Maybe some of them are actually background galaxies that have been gravitationally lensed into the foreground apparent position by intervening dark matter. Maybe the redshift estimates are wrong, and what looks like 800 foreground dwarf galaxies is actually some other population sitting at a distance that the model would comfortably explain. Maybe the alignment signal is a known systematic. Maybe. Every one of those maybes was checked. The team that produced the black window image was, by all accounts, methodical to the point of exhaustion. They ran the analysis through 3 independent pipelines. They compared their results to simulations of what artifact-laden data should look like. They cross-checked their redshift estimates using spectroscopic confirmation for a representative subsample of the 800 foreground galaxies. The spectroscopy came back clean. The galaxies are where the team said they are. They are real. The void is full. And so the second response began. The response that has been characteristic of cosmology for the past several years, as observation after observation has chipped away at the standard model. The response of careful, cautious revision. New parameters added to existing models. New physics proposed at the boundaries of plausibility. New theoretical frameworks dusted off, rewritten, and presented at conferences with a kind of restrained urgency that the field has not seen since the 1990s. One of the most active proposals to come out of the black window analysis involves an old idea given new life. The idea is called warm dark matter. To understand it, you need to understand that the standard dark matter scenario, the one built into lambda CDM, assumes the dark matter is what physicists call cold. Cold here does not mean low temperature in the everyday sense. It means the dark matter particles, whatever they are, move slowly compared to the speed of light. Slow-moving particles can clump together easily, even on small scales. Cold dark matter, therefore, produces a universe full of small structures. Dwarf galaxies should be everywhere. There should be hundreds of small satellite galaxies orbiting every large galaxy. The voids should still contain numerous small clumps of dark matter, even if they contain few luminous galaxies. The problem is that we do not see all those small structures. The Milky Way, for example, has fewer satellite galaxies than the cold dark matter model predicts. This has been known for years. It is called the missing satellites problem. There are various proposed solutions. Maybe the satellites are there, but most of them never lit up with stars, and so remain invisible. Maybe feedback from the first stars blew out the gas in small dark matter halos and prevented them from forming. Maybe the observation is incomplete, and the satellites are just below our detection threshold. Or maybe the dark matter is not cold. Maybe it is warm. Maybe the dark matter particles move just fast enough that they smooth out small-scale structure. In a warm dark matter universe, you do not get hundreds of dwarf galaxies. You get fewer. You get a population that matches what we observe in the Milky Way satellite system. The trade-off is that warm dark matter changes other predictions too. It changes the structure of voids. It changes the number of low-luminosity galaxies you should find inside them. When the black window result came in, several theoretical groups noticed something strange. The excess of foreground dwarf galaxies in the void, the excess that the cold, dark matter model could not explain, lined up almost exactly with what a particular warm dark matter scenario would predict. The dark matter particle mass that fit the observation came out to approximately 5.3 kiloelectron volts. That number is interesting because it is in the range that some particle physics theories have favored for entirely independent reasons. It is the kind of coincidence that makes a theorist sit up. Now, one observation does not overturn lambda CDM. But the black window result has reopened a question that the community had largely closed in the early 2010s. The question of whether dark matter is really as cold as the standard model assumes. Several follow-up surveys are now being planned to test the warm dark matter prediction more rigorously. If the prediction holds, the implications go far beyond a single void in the constellation sextans. The implications change what the universe is made of. They change what galaxies look like. They change the very nature of the cosmic web. But warm dark matter is only one of the proposals on the table. Another, championed by a group at the Kavli Institute for Cosmology in Cambridge, suggests that the black window's foreground excess is a signature of what they call cosmic flickering. The idea here is more speculative but in some ways more interesting. They propose that the dark energy field, the field driving the accelerated expansion of the universe, is not perfectly uniform. That it has tiny variations on very large scales, variations on the order of 1 part in 100,000, comparable to the variations in the cosmic microwave background. In regions where the dark energy field is slightly weaker than average, expansion has been very slightly slower, allowing structure to form a little more aggressively over cosmic time. In regions where it is slightly stronger, structure formation has been suppressed. If the black window happens to sit in a region where dark energy is slightly weaker than the cosmic average, then more dwarf galaxies should have formed there than the standard model predicts. The alignment signal could be explained as a long wavelength gradient in the dark energy field, leaving a coherent imprint on the orientations of low-mass galaxies across the void. The prediction is testable. If cosmic flickering is real, then we should find the opposite signature in voids in other parts of the sky. We should find voids that are emptier than average, regions where structure formation was suppressed. The Cosmos Webb Deep team has already begun planning observations of 3 additional empty fields in the southern hemisphere to test exactly this hypothesis. The data will not be available for at least another year. But the hypothesis is on the record in the literature, with predictions specific enough to be falsified. The third proposal is the one that worries researchers the most. It is also the simplest. The proposal is that there is nothing wrong with the dark matter, nothing wrong with the dark energy, nothing wrong with the standard model parameters. The proposal is that there is something wrong with our initial conditions. That the seeds of structure planted by inflation in the first fraction of a second after the Big Bang were not exactly what the simplest inflationary models predict. That there was some additional physics happening in those earliest moments, leaving a faint but coherent imprint on the universe that propagated forward through 13.8 billion years to produce exactly the kind of anomalies the black window is now showing us. To appreciate why this possibility is so unsettling, consider what it would mean. Inflation, the theory that the universe underwent a brief period of exponential expansion in its first instance, is the single piece of physics that connects the smallest scales we can imagine, quantum fluctuations at the level of individual particles, to the largest scales we can observe, the entire visible cosmos. Inflation is the bridge. It is the mechanism by which microscopic noise becomes macroscopic structure. If inflation worked exactly as the simplest models describe, then the seeds of all structure should be statistically uniform and isotropic. The pattern of galaxies and voids across the universe should look the same in every direction, on average, with no preferred orientation, no special location, no hidden order. The black window's alignment signal, if it is real and not a fluctuation, suggests that something else may have been going on during inflation, something that gave the primordial fluctuations a slight directional preference, something that violated the perfect isotropy that the simplest models assume. The technical name for this kind of deviation is statistical anisotropy. Several theoretical frameworks predict it, including certain models that invoke a pre-inflationary phase in which the universe was not yet smooth, models that include exotic fields beyond the inflaton, and models that connect to ideas about quantum gravity that we do not yet have the tools to test directly. If the black window is showing us a faint imprint of pre-inflationary physics, then we are looking at a fossil that is, in some sense, older than the universe itself. Older than the Big Bang as we usually describe it. A relic from whatever conditions preceded the inflationary epoch. The cosmologist Sean Carroll, in a public talk at the Aspen Center for Physics in the autumn of 2025, described the possibility this way. He said that for as long as we have done cosmology, we have assumed that the Big Bang erased everything that came before it, that whatever conditions existed prior to inflation were stretched away to nothing, smoothed out, made irrelevant. But what if they were not? What if some tiny residue of those pre-inflationary conditions survived, frozen into the geometry of the largest structures? What if we have been staring at that residue for years, in the patterns of the cosmic microwave background and the distribution of galaxies and the orientations of voids, and we simply did not have the resolution to see it until now? He said it with characteristic caution. He used hedging language. He noted that the evidence is far from conclusive. But he also acknowledged that the field is now seriously considering possibilities that, a decade ago, would have been dismissed as speculation. The black window did not cause this shift on its own. It is one piece of a larger pattern. The Hubble tension is another piece. The James Webb's catalog of impossibly bright early galaxies is another. The persistent anomalies in the cosmic microwave background, the cold spot, the axis of evil, the hemispherical asymmetry, are other pieces. Each one has a conventional explanation that is more or less plausible. Each one has an unconventional explanation that ties it to the others. And the unconventional explanations all converge on the same possibility, that the standard model is missing something fundamental, something that operates on the largest scales, something that was present in the earliest moments of the universe and is still leaving traces today. The black window observation has, in effect, sharpened that possibility from a vague suspicion into a concrete data point. And the data point will not go away. While the theorists argued about what the black window meant, the observers kept observing. In the months after the initial release, Webb returned to the field for follow-up imaging at additional wavelengths. The 167-hour exposure was supplemented with deep spectroscopic observations using the NIR SPEC instrument, which can split the light from individual galaxies into detailed spectra revealing their composition, motion, and physical conditions. The data from those follow-up observations began to trickle out through the second half of 2025, and each new release added another layer to the strangeness. Among the most striking follow-up findings was the confirmed detection of complex organic molecules in the gas surrounding one of the foreground dwarf galaxies. The galaxy, designated CWD 13339, sits at a redshift of approximately 0.7, meaning we see it as it was about 6 billion years ago. Its emission spectrum showed a strong signature of polycyclic aromatic hydrocarbons, the carbon-rich molecules that form in the cool envelopes around dying stars, and that are considered, on Earth, to be among the building blocks of organic chemistry. The presence of these molecules in a dwarf galaxy inside a cosmic void was not particularly surprising in itself. PAHs have been detected in many galaxies. What was surprising was the abundance. CWD 13-339's PAH emission was nearly as strong per unit of star formation as the most chemically enriched galaxies in the local universe. A small, dim galaxy in an empty pocket of the cosmos 6 billion years ago was already brewing a complex organic chemistry comparable to anything in the modern Milky Way. This shifted, subtly but unmistakably, the conversation about where complex chemistry can exist. The conventional wisdom has long been that complex molecules accumulate over cosmic time through repeated cycles of star formation and supernova feedback, with each generation of stars enriching the gas more than the last. Voids, with their slower rates of star formation, should lag behind the cosmic average. CWD 13339 was not lagging. It was keeping pace. Whatever process built up its organic inventory was running at full speed in an environment that the standard picture predicted would be a chemical backwater. The implication for astrobiology is not subtle. If complex chemistry can flourish in cosmic voids as readily as it flourishes in dense filaments, then the territory available for life is significantly larger than current estimates allow. The voids, which make up roughly 80% of the volume of the observable universe, may not be barren after all. They may host their own population of chemically rich worlds, hidden in dim galaxies that no previous survey could see. We have been assuming that the cosmic web concentrates the conditions for life. The black window data suggests that the conditions are far more widely distributed than we knew. Now, this is where it is important to be careful. The detection of organic molecules is not the detection of life. It is not even the detection of the precursors of life in any specific sense. It is the detection of carbon-rich chemistry that, on Earth, happens to participate in the chemistry that leads to life. The presence of PAHs in CWD 13339 does not mean that anything is alive in CWD 13339. It means only that the universe, even in its empty pockets, manufactures the same organic feedstock that we find everywhere else. The conclusion is modest, but it is real. And it argues against the most pessimistic versions of the rare earth hypothesis, the versions that suggest complex chemistry is itself a rare and finely tuned outcome. The follow-up spectroscopy also illuminated, somewhat, the mystery of CWD 13477, the object whose spectrum matched nothing on file. The new data did not solve the mystery, but it narrowed the possibilities. The object's spectrum, examined at higher resolution, showed 3 narrow emission features at wavelengths corresponding, after correction for redshift, to atomic transitions of nitrogen, helium, and carbon in unusual ionization states. The combination is consistent with a region of gas being illuminated by an extremely hot source, hotter than any ordinary stellar population. The dominant interpretation, though still tentative, is that CWD 13477 is what theorists have long predicted but never definitively observed: a direct collapse black hole. An object formed when, in the very early universe, a sufficiently large cloud of pristine gas collapsed directly into a black hole without first forming stars. Direct collapse black holes have been proposed for decades as a way to explain the existence of supermassive black holes at the centers of early galaxies. If you start with a stellar mass black hole, even one feeding at the maximum rate physics allows, you cannot grow it to 1 billion solar masses in less than 1 billion years. You simply run out of time. But if you start with a direct collapse black hole of, say, 100,000 solar masses already, then the growth problem becomes much more manageable. CWD 13477 may be the cleanest direct collapse candidate yet observed. Its spectrum, its redshift, its luminosity, all are consistent with the predictions of the direct collapse model. The hot gas surrounding the object would be the disk of material falling onto the newly formed black hole, illuminated by the gravitational energy released as that material spirals inward. If the identification holds up, it would be the first direct view of how the universe's largest black holes get started. It would close one of the most stubborn open questions in modern astrophysics. And it would, again, do so from inside the darkest patch of sky humanity has ever examined. A patch chosen for its emptiness, hiding inside it the answer to a question about origins. This is the recurring pattern of the black window observation. Every direction you turn, every layer of the data, every wavelength of the spectrum reveals something that was supposed to be elsewhere. The first stars are supposed to be too faint to see. The black window contains a candidate first-generation source. Direct collapse black holes are supposed to be theoretical objects. The black window contains a candidate. Complex organic molecules are supposed to be concentrated in dense star-forming regions. The black window contains a dwarf galaxy in a void that produces them as abundantly as the Milky Way does. Voids are supposed to be empty. The black window's foreground void is full, and the foreground galaxies are supposed to be randomly oriented. They are aligned. It is as though the universe, when finally pressed against a sufficiently sensitive instrument in a sufficiently empty pocket of sky, gave up its secrets all at once. Or perhaps more accurately, it had been giving up those secrets for years, in every patch of sky we examined, and we simply did not have the eyes to read them. Webb gave us the eyes. The black window was the test. And the test came back showing that the universe is more complicated, more structured, and stranger than the model we used to describe it. There is one more thread to pull before we can begin to draw this part of the story together. It concerns the most distant object in the field, CWD 13001, the candidate galaxy at redshift 16.3, and what its discovery means for the broader question of how the universe lit up. For its first roughly 380,000 years, the universe was a hot, opaque plasma. Light could not travel freely through it. Then the universe cooled. The plasma combined into neutral atoms, and the cosmic microwave background was released, the afterglow we still detect today. After that, the universe entered a period called the Dark Ages. There were no stars. There were no galaxies. There was just neutral hydrogen and helium gas, slowly cooling and clumping under the gentle pressure of gravity, occasionally illuminated by the steadily red-shifting glow of the cosmic microwave background. For hundreds of millions of years, the universe was, in the literal sense, dark. Then, somewhere between 100 and 200 million years after the Big Bang, the first stars formed. These were massive, metal-poor objects, sometimes called population 3 stars, that burned hot and died young, scattering the first heavy elements into the surrounding gas. Their ultraviolet radiation began to reionize the surrounding hydrogen, knocking electrons off the neutral atoms and gradually clearing the cosmic fog. This period, called the Epoch of Reionization, transformed the universe from a dark neutral state into the transparent, partially ionized state we see today. The transition took several hundred million years and was largely complete by about 1 billion years after the Big Bang. Until very recently, the Epoch of Reionization was one of the least observable periods in cosmic history. The relevant galaxies were too faint and too distant for previous telescopes to study in detail. We knew from the cosmic microwave background polarization data that reionization had happened. We had rough estimates of when it had started and ended, but we did not have a clean picture of what the sources of reionization actually looked like. The standard expectation was that they were small, dim galaxies, large in number, each producing a modest amount of ionizing radiation, with the total ionizing flux distributed across a large population. CWD 13001 does not fit that picture. If the redshift is correct, then 220 million years after the Big Bang, the universe already contained a galaxy bright enough to detect across 13.5 billion years of expansion. It was not small. It was not dim. It was already producing massive star formation, and according to the spectral analysis, it was already producing the heavy elements that mark the chemical fingerprint of multiple generations of stellar evolution. Either the first stars formed earlier than we thought, leaving time for several generations to live and die before CWD 13001 came into being, or the standard model of stellar evolution does not apply cleanly to the very first stars, and the timescales were compressed by physics we do not yet understand. A theoretical framework that has been gaining attention in response to the steady accumulation of bright early galaxies is one in which the first stars were not just massive, but supermassive, with masses of thousands of solar masses burning so hot and so fast that a single one of them could enrich an entire proto-galactic cloud with heavy elements in just a few million years. Such supermassive first stars are speculative. They have not been definitively observed. But the spectral signatures expected from them, including unusually strong nitrogen emission and rapid chemical enrichment, are precisely what we are starting to see in the most distant galaxies that Webb has imaged. CWD 13001 may be the cleanest example yet of a galaxy whose first stars went big, went fast, and produced a fully evolved chemistry in a tiny fraction of the time the standard model expected. If this picture holds, then the Dark Ages were shorter than we thought. The universe lit up earlier, brighter, and more abruptly than the textbooks describe. The transition from neutral darkness to ionized transparency was not a slow, gradual fade. It was, in the language of one of the researchers involved in the black window analysis, a flash. A cosmic ignition that happened with surprising speed once the first generation of stars got going. The implications for everything downstream, for the chemistry of the early universe, for the formation of the first dwarf galaxies, for the conditions under which life could have first become chemically possible, ripple outward. This is, in some ways, the most poetic finding from the black window. We pointed our most powerful telescope at the darkest patch of sky we could find, and we discovered that the darkness contained the moment the universe first chose to be bright. That is not a small finding. It is the kind of finding that will reshape textbooks. It is the kind of finding that 20 years from now, will be cited as the moment our understanding of the early universe pivoted. But it is also a finding that, in the present moment, the researchers themselves are still struggling to fully accept. Because if it is correct, if the first stars really were supermassive and the universe really did ignite that quickly, then a number of cherished assumptions in modern cosmology do not survive contact with the data. The slow assembly model of galaxy formation does not survive. The gradual reionization picture does not survive. The textbook timeline of the Dark Ages does not survive. And what replaces them is not yet clear. Several competing frameworks are circulating in preprints and conference talks, each addressing some subset of the anomalies. None addressing all of them tentative, all of them subject to revision as new data arrives. We are in the early days of a reconstruction. And the reconstruction is being driven not by theory pushing observation, as has often been the case in physics, but by observation overwhelming theory. The instruments are now sensitive enough that they are finding things the theorists had not even thought to predict. The data is in front of us. The understanding has not caught up. This is, in many ways, the most exciting state a science can be in. It is also the most disorienting. Researchers who have spent their entire careers building intuition around lambda CDM are finding that their intuitions are no longer reliable. Graduate students entering the field today will spend their careers, very possibly, in a different model. The senior generation of cosmologists is, by all accounts, divided between excitement and dismay. The excitement is that genuinely new physics may be on the horizon. The dismay is that the model that worked so beautifully for so long is no longer working everywhere we look. And the black window has, perhaps more than any other single observation in recent years, concentrated all of these tensions into one field of view. One patch of sky, the size of a grain of sand at arm's length, containing a record number of anomalies. A galaxy too bright at too early an age. An object whose spectrum matches no known category. A foreground void too full of galaxies. An alignment that should not exist. Complex chemistry in dim, isolated systems. Each of these is a strand. Together they weave into a question that the field is now openly grappling with. The question is not whether the universe is bigger than we thought. We knew it was. The question is not whether dark matter exists. We are reasonably sure it does. The question is not whether dark energy exists. The evidence for accelerated expansion is robust. The question is something deeper. The question is whether the universe is more layered than we imagined. Whether beneath the cosmic web we have mapped, beneath the dark matter halos we have inferred, beneath the dark energy field whose effects we have measured, there is another layer of structure, another set of organizing principles that we have only just begun to detect. If there is, the black window is one of the first windows into that layer. And the view through it is going to keep us busy for decades. But the layered architecture of the universe, if that is really what we are looking at, raises a question that goes beyond physics. It is a question about ourselves. Because if the standard model that has guided us for 25 years is breaking down at the edges, if the dark places are not empty, if the universe contains structure on every scale we can imagine, including scales we have not yet learned to see, then our place within it is also more complicated than we knew. We are not just observers of a simple, smooth, homogeneous cosmos. We are observers inside one of the rare, luminous threads of a much more elaborate fabric. And that fabric, as the black window has begun to suggest, may have been woven by physics that operates on scales and in regimes we have not even started to seriously study. There is a humbling thought in that. There is also, depending on how you choose to receive it, a thrilling one. Because if the universe is more layered than we thought, then the next generation of telescopes, the next round of observations, the next decade of analysis is not going to be a matter of refining numbers. It is going to be a matter of discovering structures, real architecture, real physics that nobody yet has the equations for. The dark places of the sky, the places we have been writing off as empty for 100 years of modern astronomy, are about to become the most interesting places in the universe to look. They are going to be where the next discoveries come from. And the black window, this one patch of sky in the constellation Sextans, this one 167-hour exposure made by a telescope 1,000,000 miles from Earth, is going to be remembered as the place where we first realized it. We still have not seen the strangest thing in the black window data. We still have not talked about the gravitational lensing anomaly. We still have not talked about the surprising radio counterpart that one of the foreground sources turned out to possess. We still have not talked about the curious dimming pattern that one of the team members noticed when comparing the Webb data to archival observations from the same patch of sky taken with previous instruments. Each of these is its own thread. Each of these adds another piece to the picture. And each of these, taken with the others, deepens the conclusion that the dark region of the sky we pointed at last winter is not a dark region at all. It is one of the brightest places in the cosmos. We just needed the right instrument to see it. So let us turn to those remaining threads. Let us continue down into the depth of the black window, into the layers Webb peeled back one by one as the data accumulated, because each layer carries a different fingerprint. Each layer tells us something about how the universe is structured at a different scale and a different time. And together they paint a picture that is, more than anything else, an invitation. An invitation to look harder, to look longer, to look at the places we have always assumed contained nothing, because the universe has been hiding its most important secrets exactly there. The gravitational lensing anomaly is, in some ways, the most technically interesting of the remaining findings. It came out of an analysis performed by a postdoctoral researcher named Elena Voss, working at the Max Planck Institute for Astrophysics, who decided in the spring of 2025 to take the black window data and run it through a lensing detection pipeline. The pipeline was originally designed to find weak gravitational lensing signatures in deep survey data. Weak lensing is the subtle distortion of the shapes of background galaxies caused by the gravity of intervening matter. The distortions are tiny, typically a fraction of a % change in the apparent ellipticity of each background galaxy. To detect them statistically, you need a large number of background galaxies and a careful analysis that averages out the random orientations of individual galaxies, leaving only the coherent distortion pattern induced by the lensing mass. When Voss ran the black window data through her pipeline, the result was unexpected. The weak lensing signal across the foreground void was not zero. Voids, with their underdense matter content, should produce a weak negative lensing signal, slightly anti-distorting background galaxies, as light from those galaxies passes through the region of below-average density. The black window void did show such a signal, but the signal was less pronounced than the standard model predicted. The void was lensing more than it should have, given its apparent matter content. The interpretation, after several months of analysis, was that the void contains more matter than the visible galaxy count suggests, not enough to make the void no longer a void, but enough to soften its underdensity. Enough to imply that some matter, some substance, some component of the universe is present in the black window void that is not being accounted for by the catalog of luminous sources we can see. The component is, in some sense, dark. Dark in the sense that it does not emit light at any wavelength Webb can detect. Dark in the sense that it has been missed by every previous survey. Dark in the sense that its presence is inferred only from the gravitational fingerprint it leaves on the light passing through it. Voss spent the next several months trying to characterize what she had found. She mapped the lensing signal across the void in fine spatial detail. She compared its distribution to the catalog of luminous galaxies in the foreground. And she discovered something that, once she had drawn the map, was immediately obvious. The excess lensing signal was not distributed uniformly across the void. It was concentrated. It traced a structure. The structure was diffuse, faint, and elongated, but it was unmistakably present. The void contained, threading through its interior, a kind of ghost. A filament of dark mass, perhaps 100 million light-years long, running through what was supposed to be empty space, leaving no luminous trace, detectable only by its gravity. When Voss presented her findings at a workshop at the Kavli Institute in late 2025, the room was full of people who had been waiting for exactly this kind of result. The existence of dark filaments threading through cosmic voids had been predicted by several theoretical frameworks for over a decade. The predictions were a natural consequence of certain dark matter models, in which the dark matter component is slightly less coupled to the visible matter component than the standard model assumes. In those frameworks, the dark matter does not always follow the galaxies. It can form its own networks. It can run through the voids the way blood vessels run through tissue, invisible until you have the right instrument to see them. What nobody had been able to do before the black window. was actually detect such a filament. The signals were too faint, the data too sparse, the analysis too dependent on assumptions that the data could not constrain. The black window changed that. With 167 hours of Webb integration time, with thousands of background galaxies behind a single carefully chosen void, Voss had the statistical power to do the analysis cleanly. And the answer the analysis returned was unambiguous. There is a dark filament in the black window void. It is real, it is gravitationally massive, and it is doing exactly what the prediction said it should do. If this is typical, if dark filaments thread through every cosmic void, then the mass budget of the universe shifts, not by much. The total amount of dark matter is reasonably well constrained from other measurements, but the distribution of that dark matter, the question of where it actually is, changes meaningfully. A portion of the cosmic dark matter inventory may be located inside the voids, not just around them. The cosmic web may be denser in dark matter terms than the visible map of galaxies suggests. The voids may not be voids at all, in any complete physical sense. They are luminous voids. They are voids only with respect to the matter that emits light. With respect to the matter that does not emit light, they are not empty. They are threaded. They are crossed by invisible structures that connect distant clusters through what looks, on every previous survey, like nothing. This is, in its way, a profound rearrangement of the picture of the cosmos that humanity has carried for the past few decades. The picture in which the universe is divided cleanly into dense regions and empty regions, into nodes and voids, into structure and absence. The new picture, the one the black window is beginning to reveal, is more layered. The dense regions are still there, the empty regions are still there in terms of luminous matter. But threading through and between them is a hidden architecture, a network of dark mass that follows its own logic, and that connects parts of the universe we had previously believed to be separate. Sean Carroll, in a follow-up essay published shortly after Voss's presentation, described this as a moment of reframing rather than discovery. He pointed out that the existence of dark filaments and voids was not strictly new physics. The standard cold dark matter model, taken seriously and run through enough simulations, does predict such structures. What was new was that we now had evidence for them. Direct, statistically robust evidence from a specific patch of sky. And once you have evidence, your picture of the universe changes whether you wanted it to or not. The voids, in his words, have been promoted from settings to characters. They are no longer the background against which structure forms. They are part of the structure. They have geometry. They have content. They have stories of their own. While Voss was working on the lensing, another team was investigating a different anomaly in the black window data. A radio survey of the same patch of sky had been conducted in parallel with the optical observations, using the upgraded version of the Very Large Array in New Mexico, in coordination with the Webb Deep Field campaign. The radio data was intended as a complement to the infrared, giving researchers a multi-wavelength view of the field. Most of the radio sources detected were exactly what astronomers expected: bright active galactic nuclei in the background, star-forming galaxies at moderate redshifts. The usual catalog of radio-bright objects that any deep field contains. But one of the foreground dwarf galaxies, one of the 800 unexpected sources sitting in the supposedly empty void, had a radio counterpart. And the radio emission was strong. Strong enough that, in isolation, the radio source would have been classified as an active galactic nucleus, a supermassive black hole feeding rapidly at the center of a galaxy and powering a relativistic jet of high-energy particles. The problem was that the host galaxy was a dwarf, a small, dim, low-mass system. Dwarf galaxies are not supposed to host active, supermassive black holes of the kind that produce powerful radio emission. The conventional picture is that supermassive black holes scale with the mass of their host galaxies. Big galaxies host big black holes. Small galaxies host small black holes, if they host any at all. The black window dwarf with the radio counterpart, designated CWD 13211, did not fit this picture. The mass of the host galaxy, as inferred from its luminosity and chemical signatures, was approximately 100 million solar masses, comparable to one of the Milky Way's smaller satellites. The mass of the black hole, as inferred from the radioluminosity, was at least 10 million solar masses. Roughly 10% of the entire host galaxy's mass was in the central black hole. For comparison, the Milky Way's central black hole is about 4 million solar masses. The Milky Way's total mass is about 1 trillion solar masses, including dark matter. The black hole is roughly 4 parts in a million of the host galaxy. CWD 13211's central black hole is, by mass ratio, about 20,000 times more dominant than ours. This is not how galaxies are supposed to form. The standard model of galaxy formation predicts that galaxies and their central black holes grow together, with the black hole accreting mass at a rate that is gravitationally and energetically tied to the host's star formation. The two should remain in a rough proportion throughout cosmic history. Galaxies with disproportionately massive central black holes should be rare, and the ones we have found in the local universe have all turned out to be galaxies that were stripped of their outer stellar envelopes by past gravitational interactions. They had been bigger once. Their black holes had grown when the galaxies were larger. The disproportion was the legacy of past disruption. CWD 13211 has no obvious history of disruption. It sits inside a void. Voids are the quietest dynamical environment in the universe. There are no nearby galaxies to have stripped its outer envelope. There has been no recent interaction to explain why the central black hole is so dominant. The galaxy looks, to all observational appearance, like it has been undisturbed for billions of years. And yet it harbors a black hole that, by the standard model, should not exist in a galaxy of that size. This raises another possibility, one that has begun to find serious traction in the literature. The possibility is that supermassive black holes can form, in some cases, independently of their host galaxies. That they are not always grown by feeding from the central regions of the galaxies they inhabit. That some of them form first, perhaps through the direct collapse process that CWD 13477 may also be illustrating, and only later acquire a galaxy that gathers around them. In this picture, the black hole comes first. The galaxy is the consequence. If this is the correct interpretation for CWD 13211, then the cosmic voids may be the natural habitat for these kinds of objects. A direct collapse black hole formed in a low-density region of the early universe, with relatively little surrounding matter, would grow slowly. It would gather only a small galaxy around it because there was not much gas available to fall in. The galaxy that formed would be a dwarf, but the black hole, having been born already massive, would dominate the system. A small galaxy with a disproportionately large central black hole sitting in a cosmic void is exactly what this scenario predicts. The black window may have given us the cleanest example yet observed. The implications, again, ripple outward. If supermassive black holes can form independently of their host galaxies, then the demographic picture of black holes in the universe shifts. Some of them may be hidden in dwarf galaxies that previous surveys could not detect. Some of them may be sitting in apparently empty regions of space, doing very little, occasionally flaring up when material happens to fall in. The total population of supermassive black holes may be larger than current estimates, and they may be distributed differently than the galaxy-centric picture would predict. This in turn has implications for everything from the cosmic gravitational wave background, which is partly produced by the merger of supermassive black holes, to the rate of luminous transients detectable in nearby galaxies, to the question of how much of the universe's central mass is concentrated in objects that we have not yet learned to find. The third remaining thread, the dimming pattern, came from a comparison that nobody had thought to make until one of the junior researchers on the Cosmos Webb Deep team, a graduate student named Akira Tanaka at the University of Tokyo, noticed something curious. The black window region had been imaged in shallower exposures by previous instruments going back about 20 years. The earliest deep observation of the field had been made with a ground-based survey telescope in 2005, with subsequent observations in 2013 and 2019 using different instruments. None of the previous observations had been deep enough to detect the foreground dwarf galaxies that Webb had now found. But several of the brighter foreground sources, the ones at the upper end of the dwarf galaxy luminosity range, had been detectable in the earlier surveys, just barely. Tanaka decided to do a temporal comparison. He took the Webb measurements of the brightnesses of these sources and compared them to the brightnesses recorded in the older surveys, adjusting for the different instruments and filter passbands. What he found, after several months of careful work, was a subtle but statistically significant pattern. A subset of the foreground galaxies appeared to have dimmed measurably between 2005 and 2024, not all of them. About 15% of the sample showed a downward trend in luminosity. The trend was small, a few percent over 20 years, but it was consistent across multiple sources. In the same region of sky, over a baseline that was just long enough to detect. When Tanaka first showed his analysis to his advisor, the advisor's response was, quite reasonably, skepticism. Galaxies do not dim measurably over 20-year timescales. Their stellar populations evolve over hundreds of millions or billions of years. Their gas content shifts on timescales of tens of millions of years. 20 years is nothing in the life of a galaxy. There had to be some systematic error in the cross-calibration of the different instruments. There had to be something the analysis was missing. Tanaka redid the analysis. He used 3 different cross-calibration methods. He restricted his sample to sources observed with the most similar filters. He accounted for every known instrumental effect. The dimming signal persisted. It got slightly weaker as more conservative cuts were applied, but it did not go away. By the time Tanaka's preprint appeared in early 2026, the analysis had been through enough independent checks that the dimming had to be taken seriously. The question was no longer whether it was real, but what was causing it. The answer, as with so much else in the black window data, is not yet clear. Several hypotheses are being explored. One is that the dimming sources are dwarf galaxies, whose star formation has been quenched, in real time, by some kind of environmental process specific to voids. Another is that the sources contain transient or variable populations of stars, and that the apparent dimming is the result of those populations entering a quieter phase. A third, the one that has attracted the most attention precisely because it is the most heterodox, is that the dimming is not intrinsic to the galaxies at all. It is the result of something between us and them. Something in the foreground. Something absorbing or scattering light from sources behind it. What could absorb light coherently across a void? The standard answer is intergalactic dust, but voids are supposed to be relatively clean of dust. The amount of dust required to produce the observed dimming, distributed across the black window void, is uncomfortable. It is more than the standard model allows. If the dimming is being caused by foreground material, then voids contain more diffuse intergalactic medium than we had estimated. The voids are not clean. They have content. They have absorption. They scatter light. A more speculative possibility, one that has not yet made it into formal publications but that has been raised in informal conversations at conferences, is that the dimming might be related to the dark filaments. The same hidden architecture that Voss detected through gravitational lensing might also be associated with diffuse, low-density gas that we have not yet been able to detect directly, but that is sufficient to produce a small amount of foreground absorption. If this is the case, then the dark filaments are not purely dark. They are dim. They have a gas component, too low in density to glow visibly but high enough to absorb a measurable fraction of background light. And the gas component would be made of, presumably, ordinary baryonic matter. Hydrogen, helium, traces of heavier elements. The same stuff that everything else in the universe is made of, just spread thin enough that we have not previously had the sensitivity to see it. If this is correct, then we may have just located a portion of the cosmos's missing baryons. For decades, cosmologists have known that there is a discrepancy between the amount of ordinary matter the universe is supposed to contain, based on the cosmic microwave background and Big Bang nucleosynthesis calculations, and the amount of ordinary matter we have been able to find in stars, gas, and dust. The discrepancy is real. The universe should contain more ordinary matter than we observe. The missing baryons problem has been one of the lingering puzzles of modern cosmology. The proposed solutions have generally involved diffuse hot gas in intergalactic space, in regions that are difficult to observe directly. The black window's faint absorption signal may be the first detection of a portion of that missing matter, sitting in a place nobody had thought to look, hidden inside a void, threading along the dark filaments. Quiet enough to have escaped notice until a telescope sensitive enough to see it was pointed at exactly the right patch of sky. This is the pattern. Every layer of the black window data, when examined carefully, reveals something that fills in a gap in our understanding. The bright early galaxy filling in the gap of when reionization started. The exotic spectral source filling in the gap of how supermassive black holes get their start. The unexpected foreground population filling in the gap of where the universe stores its low-mass galaxies. The dark filaments filling in the gap of how dark matter is distributed in apparently empty space. The disproportionate central black hole filling in the gap of whether black holes always grow with their galaxies. The dimming pattern filling in the gap of where the missing baryons might be. Each of these is a major finding in its own right. Any one of them would, in a less crowded year, be the headline result of a major observational campaign. The Black Window produced all of them simultaneously from a single 167-hour exposure of one patch of sky. The data is still being analyzed. New findings are still emerging. As of the most recent updates from the team, 3 additional anomalies have been identified that have not yet been publicly described in detail, because the researchers want to be confident in their analysis before making them public. This is the state of the field. A single observation, in the darkest patch of sky humanity has ever deliberately examined, has produced enough strangeness to keep cosmology busy for a decade. And the natural next question is whether the Black Window is unique or whether it is representative. Is this patch of sky special? Or are all the dark regions hiding similar populations of small galaxies? Similar dark filaments, similar misfit objects, similar evidence that the standard model is incomplete. The Cosmos Webb Deep team has plans to find out. As mentioned earlier, 3 additional empty fields in the southern hemisphere are slated for deep imaging campaigns over the next 2 years, with the goal of replicating the Black Window analysis in independent samples. If the same anomalies show up in those fields, then the conclusion is unavoidable. The Black Window is typical. Every void in the universe contains similar hidden structure. The standard model needs to be revised, and the revision needs to account for all of these signatures simultaneously. If the anomalies do not show up in the new fields, then the Black Window may be a statistical outlier. A particular patch of sky that happens to contain features that other patches do not. In that case, the conclusions would be more limited. The Black Window would still be remarkable. It would still be a useful test of theoretical predictions. But it would not by itself require a wholesale rethinking of cosmology. The honest expectation, the one that most researchers in the field are quietly carrying, is that the anomalies will not disappear in the new fields. The patterns are too coherent, too well aligned with multiple independent theoretical predictions, too consistent with the steady accumulation of other tensions in the standard model to be a statistical accident. Within the next 2 to 3 years, we will know whether the Black Window's findings are typical. And the betting consensus, insofar as such a thing exists, is that they will be. But what then? If the dark regions of the universe are full of hidden structure, if voids contain dark filaments and low-mass galaxies and disproportionate black holes, if the cosmos is layered in ways the standard model does not predict, what do we do with that knowledge? What does it mean for the broader picture of where we are and what we are doing here? The answer, in scientific terms, is that we have a lot of work ahead of us. New surveys, new instruments, new theoretical frameworks, new computer simulations. The next generation of telescopes, the extremely large telescope under construction in Chile, the square-kilometer array spread across Australia and South Africa, future space-based platforms still in design, are all going to be pressed into service to extend and refine what the Black Window has begun to show us. We are going to map the dark filaments in detail. We are going to inventory the dwarf galaxy population of the cosmic voids. We are going to push the catalog of direct collapse black hole candidates from a single tantalizing source to a statistical sample. We are going to constrain the warm dark matter parameter space until either it converges on a definitive value or it is ruled out in favor of some other framework. We are going to test whether the alignment signal is a tidal effect, a magnetic effect, or a signature of pre-inflationary physics. We are going to do, in short, a great deal of patient, careful, slow work over the next several decades to turn the Black Window's strangeness into a coherent, revised understanding of the cosmos. But there is another dimension to what we do with this knowledge, a dimension that lies outside the formal apparatus of science and inside the broader question of what it feels like to live in a universe that turns out to be different from the one we thought we lived in. For most of human history, our cosmologies have been small. They have placed us at the center of a manageable creation. The sky was a dome. The earth was the floor. The stars were nearby. Heaven was just above. Hell was just below. Even after the Copernican revolution moved Earth from the center, even after Galileo's telescope showed that Jupiter had moons of its own, the universe remained, in the popular imagination, a comprehensible place. The stars were many, but they were stars. The planets were a few, but they were known. The structure of reality was something a person could hold in their head, with effort, and feel that they understood. That picture has been in steady retreat for the past 100 years. Each new generation of telescopes has expanded the cosmos and complicated it. The discovery of other galaxies in the 1920s. The discovery of cosmic expansion. The discovery of the cosmic microwave background. The discovery of dark matter. The discovery of dark energy. The discovery of the cosmic web. Each step has added another layer of structure, another category of stuff, another dimension of strangeness. And each step has, in its way, made the universe a less comfortable place to live in. Not less beautiful, not less remarkable, just less personal, less ours. More its own thing, indifferent to the species that happens to be looking at it from a small rocky planet around an ordinary star. The black window continues that tradition. It has not made the universe smaller. It has made it larger, in a sense that does not depend on physical size. It has revealed that the universe is hiding things in places we had assumed contained nothing. It has shown us that the emptiness is full. It has shown us that the structure we thought we understood goes deeper than we knew. And it has invited us, gently and persistently through the medium of the data itself, to revise our picture once again. The revision is humbling. It is also in its way exhilarating, because every time the universe turns out to be more complex than we thought, it offers us more to discover, more to study, more to understand. The black window has given us, in a single observation, enough new questions to power the careers of an entire generation of cosmologists. The questions are real, the data is solid, and the work is going to be extraordinary. There is one more thread we have not yet pulled. It concerns the question of whether the black window is, in any meaningful sense, looking back at us. Not in a literal, observational sense. The black window contains no detected civilizations, no artificial signals, no evidence of intelligence. The Cosmos Webb Deep Team has not claimed any such detections, and no plausible candidates have emerged in the data. But there is a more subtle sense in which the question matters. The black window contains 13,000 galaxies. Each galaxy contains hundreds of billions of stars. Each star is potentially attended by planets. Each planet is potentially capable of hosting chemistry, and some fraction of that chemistry may, given time, develop into something more. If even a tiny fraction of the planetary systems hidden inside that one patch of sky have produced anything resembling life, then the number of inhabited worlds inside the black window alone is enormous. The number of conscious observers, if any of them have produced conscious observers, is enormous. And every one of those observers, if they exist, is looking out at their own night sky, seeing their own version of the cosmic darkness, asking their own version of the same questions. Why is the universe the way it is? Why are we here? What is hidden in the dark? The black window does not give us the answer to those questions, but it gives us a strange new piece of context. It tells us that wherever those observers are, wherever they live, whatever their sky looks like from their particular vantage point inside one of the 13,000 galaxies in the field, they are inside a cosmos that hides structure inside its emptiness. They are inside a cosmos in which the voids are not voids. They are inside a cosmos whose simplest pictures, the ones most likely to be developed by any reasonably advanced civilization at the early stage of its astronomy, are going to turn out to be incomplete. They will, eventually, build their own version of the James Webb Space Telescope. They will point it at their own darkest patches of sky. And they will discover, as we just have, that the darkness was never empty. This is, in a sense, an inheritance. Every observer in the cosmos who reaches a certain level of observational sophistication is going to learn the same lesson. The dark regions are full. The simple models are incomplete. The universe is layered in ways the early frameworks miss. The lesson is, presumably, universal. It is one of the things that any civilization that develops sufficiently powerful telescopes will eventually figure out. We are simply, perhaps, the first such civilization in this corner of the cosmos to do so. Or, perhaps, not the first. Perhaps somewhere out in the field of the Black Window, in one of the 13,000 galaxies whose light has been traveling toward us for billions of years, there is a civilization that figured all of this out long before we did. That mapped its own version of the cosmic web. That detected its own version of the dark filaments. That looked into its own dark patches of sky and learned the same lessons we are learning now. If such a civilization exists, then their light is not in the Webb data. Civilizations do not appear in infrared imaging of distant galaxies. They are too small. Even an entire technological civilization spread across an entire planet would be invisible in the data. The galaxies we are seeing are the backdrop. Whatever lives inside them, whatever has lived inside them across the 11 or 12 or 13 billion years of their light's journey toward us, is hidden inside the imagery, indistinguishable from the rest of the galaxy's light, but it would still be there. And the thought, however speculative, has its own gravity. We pointed a telescope at the darkest patch of sky we could find. We let it stare for 167 hours. The light that returned to us was billions of years old. It contained, possibly, the spectral signature of countless worlds, countless biospheres, countless conscious beings, all reduced to the diffuse glow of distant galaxies. We could not resolve any of them, we could not extract any of them, but they may have been there, encoded into the light, looking back at us in the indifferent way that history always looks back at the present, already gone, already changed, already perhaps lost to processes we have not yet understood. The Black Window is, in this sense, not just a window into the cosmos. It is a window into time. And the longer we look at it, the more we realize that what we are seeing is not a static picture of the universe as it is, but a layered record of the universe as it was, at every depth, at every distance, at every age. The most distant galaxies in the field show us the universe as it was 220 million years after the Big Bang. The intermediate galaxies show us the universe in its middle age. The foreground galaxies show us the recent universe, the cosmos as it was when our planet was already forming, when our species had not yet appeared, when the conditions for the things we recognize as our own world were still being assembled, and all of it, the entire stack of cosmic history, was contained in a patch of sky we had previously dismissed as empty, not just contained, hidden, quietly preserved, waiting for an instrument sensitive enough to read it. The James Webb Space Telescope, after a quarter-century of development and 1,000,000 miles of travel from Earth, was that instrument. The 167 hours of integration time was the reading. The data we now have is what the universe was holding for us, in that one patch of dark sky, all along. We are not done with it yet. The data archive will continue to yield results for years. New analysis pipelines will find things the original team missed. Theoretical frameworks will be tested and refined and replaced. The Black Window will be reanalyzed many times, with each pass extracting a little more meaning, a little more context, a little more of the story. And in the meantime, the team will continue with its plan. 3 more deep fields in the south. Comparisons to other voids. Extensions to even longer exposure times. Cross-correlations with future observations from other instruments. The Black Window is only the beginning of a campaign. It is the first move in a much larger investigation that will, if everything goes as planned, redefine our understanding of what cosmic voids are, what they contain, and what they mean for the broader picture of how the universe is structured. What we already have, even at this early stage, is enough to begin reframing some of the deeper questions cosmology has been carrying for decades. The Hubble tension, the disagreement between the two ways of measuring the expansion rate of the universe, has been one of those questions. The standard interpretation has been that one of the measurements must be wrong, that some hidden systematic effect must be biasing either the early universe value or the late universe value, and that future observations will eventually reveal the source of the discrepancy. The Black Window suggests a different interpretation. If voids contain more matter than we previously thought, in the form of dark filaments and hidden dwarf populations, then the local universe is, in some places at least, less empty than the standard model assumes. And if the local universe is less empty, the relationship between local expansion measurements and the cosmic average changes. Not by much, but possibly by enough to account for a portion of the Hubble tension. This is, again, speculative. The black window data alone cannot resolve the Hubble tension. But it adds another data point to a growing pattern. The pattern is that the simple, smooth, uniform universe assumed by the cleanest versions of the standard model is not what we actually observe. The universe is lumpy on scales we did not previously appreciate. The lumpiness affects our measurements in ways we are only just beginning to model. And the resolution of the Hubble tension, if and when it comes, is likely to involve a more sophisticated treatment of how local conditions influence the values we extract from local data. The same pattern shows up in the persistent anomalies of the cosmic microwave background. The cold spot in the constellation Eridanus, which we mentioned earlier, has a slightly elevated probability of being associated with a large foreground void in roughly the same direction. The cold spot has been one of the puzzles of CMB cosmology for 2 decades, and several explanations have been proposed, but no consensus has emerged. The black window result, while not directly about the Eridanus cold spot, does change the context of the puzzle. If voids in general contain more matter than the simplest models predict, in the form of distributed dark mass that the simplest models do not account for, then the calculation of how much CMB cooling a given void should produce changes. The cold spot may be explainable without invoking new physics, simply by accounting for the matter content of the void that produces it. Or it may not. The question is open. But the black window has given researchers a new tool for addressing it. And then there is the largest question of all, the question of what the universe is actually like, on the largest scales, in regions we have not yet observed in detail. The standard cosmological principle states that the universe, viewed on scales of about 300 million light-years or more, is statistically the same in all directions. This is the assumption that allows cosmologists to use the data from one part of the sky to make inferences about the universe as a whole. The cosmological principle has been one of the foundations of modern cosmology, and it has been confirmed broadly by every major observation we have made. The cosmic microwave background is uniform to 1 part in 100,000. The distribution of galaxies, averaged over sufficiently large scales, is isotropic. The expansion rate, measured in different directions, agrees within the precision of our instruments. But the black window's alignment signal, if it holds up, is a faint hint that the cosmological principle may not be perfectly true. The alignment is small. It is detectable only with the kind of precision that Webb provides, in a kind of analysis that previous surveys could not perform. But it is there. And if the universe contains a preferred direction, even a very faint one, the implications for cosmology are large. They are not catastrophic. The cosmological principle would still be approximately true. The standard model would still work, broadly, for most calculations. But the corrections would matter for the most precise measurements. And the existence of any preferred direction at all would tell us something important about the conditions in which the universe began. We have not confirmed this yet. We may not confirm it for years. The follow-up observations of the 3 additional southern fields will be one test. Further analysis of existing surveys will be another. The future generation of cosmological probes, which will measure galaxy distributions and alignments across vast volumes of the sky, will be a third. By the end of this decade, we will probably know whether the black window's alignment is a real feature of the universe or a statistical accident. And if it is real, the conversation about cosmology will shift in ways that are difficult to fully anticipate now. This is the work that lies ahead. It is a lot of work. It will take a long time. The black window has not given us answers so much as it has given us a much sharper, much more detailed set of questions. Questions that we now have the instruments to address. Questions that, 20 years ago, we would not have known how to ask. And in the meantime, while the work proceeds, the rest of us are left with the image. The 167-hour exposure of a patch of sky the size of a grain of sand at arm's length, in the constellation Sextans, in a direction that, for most of the history of human astronomy contained, as far as anyone could tell, nothing at all. The image is now public. It has been released to the scientific community and to the public alike. You can find it online if you look. It is a deep field, like the Hubble deep field before it, but more layered, more textured, more crowded than any deep field before. It is the deepest view into the universe humanity has ever assembled. And it shows that the universe is not empty anywhere, that the darkness is not dark. That in every direction we look, no matter how carefully we choose the emptiest, quietest, most featureless patch of sky we can find, we find more. There is a phrase that several of the researchers involved in the black window analysis have used, almost identically in interviews and conference talks. They describe the experience of working with the data as one of being surprised in slow motion. The data did not deliver a single dramatic revelation. It delivered a steady, persistent series of small surprises, each one slightly more disorienting than the last, accumulating over months until the cumulative effect became overwhelming. By the time the team began drafting the major papers, they had been living inside the dataset for nearly a year. Their intuitions about what to expect from a deep field had been steadily revised. Their sense of what voids were supposed to look like had been steadily upended. And when they finally stepped back and looked at what they had found, the experience was, in the words of one team member, the closest thing she had ever had to a religious experience inside her own discipline. Not because the data was supernatural, it was entirely natural, but because the natural world had turned out to be, once again, larger and stranger than the framework she had been using to describe it. This is the experience that Hidden Beyond Stars exists to share with you. Not the certainty that science sometimes seems to promise, the opposite of that certainty. The deep, abiding strangeness of a universe that keeps revealing itself to be more than we had assumed, in directions we did not know to look. The black window is one of the most striking recent examples of that strangeness. But it is also part of a much longer pattern. The pattern of every generation of telescopes finding that the universe is richer than the previous generation realized. The pattern of every careful observation reshaping the framework that prepared us for it. The pattern of the cosmos refusing, with great patience, to be smaller than it actually is. We are, in this moment, only at the beginning of understanding what the black window has shown us. The papers will continue to come out. The analyses will continue to refine. New observations will extend, complicate, and sometimes overturn the preliminary conclusions. The story will change in the telling, as all scientific stories do. The specific numbers will be revised. The specific interpretations will compete. Some of the most exciting claims will turn out to be incorrect. Other claims, currently too speculative to be made publicly, will turn out to be the real signal hidden in the noise. The process of figuring out which is which will take time, and the people doing the work will deserve our patience. But the broad outline is, at this point, fairly clear. We pointed our most powerful telescope at the darkest patch of sky we could find. We let it stare for over a week. The data that came back contained galaxies older than the standard model said could exist. Foreground galaxies in numbers that voids should not contain. Alignments that should not be present. Dark filaments threading through what was supposed to be empty space. Disproportionate black holes inside dwarf hosts. And a faint dimming pattern hinting at a population of missing matter that we have been looking for, in vain, for decades. We found these things not because we were searching for them. We found them because we looked at a place where we had assumed there was nothing, and the nothing turned out to be everything. This is, when you let it settle, a profound thing to know about the universe. It changes the texture of how you think about empty space. It changes the way the night sky looks when you stand under it. The black gaps between the stars, the dark patches your eye glosses over when it scans the heavens, the parts of the sky that look like absence are not absent. They are full of things you cannot see, structures you have not been taught to look for. Populations of galaxies dimmer than any star, threading through the darkness with a quiet architecture that the standard maps of the cosmos do not yet show. The darkness, properly understood, is the most interesting part of the sky. The darkness is where the next generation of discoveries is going to come from. The darkness is, in a sense, the part of the universe that has been hiding from us, patiently, throughout the history of human astronomy, until we finally built the eye that could see it. And we have built that eye. It is sitting 1,000,000 miles from Earth, orbiting the second Lagrange point, kept cold by a sunshield the size of a tennis court, returning data every day. It is going to look at many more dark patches of sky in the coming years. It is going to extend the black window catalog into the dozens. It is going to confirm, or reject, or complicate every preliminary finding we have just walked through. The story we have told tonight is, in 5 years, going to look different. In 10 years, it will look very different. In 20 years, it may look almost unrecognizable. The basic conclusion, that the universe is layered in ways the simplest models miss, will likely remain. The specific structures, the specific numbers, the specific names of the candidate objects will all evolve as the data improves. This is how science works. It is not a finished cathedral, it is a construction site. The building is going up. The plans are being revised as the work proceeds. The materials are being discovered in real time. The black window is one of the most significant deliveries of material that the construction site has received in years. And the work that follows from it is going to keep cosmologists busy for the rest of their careers. What does this mean for us? For the people who are not cosmologists, who are not going to spend the next decade arguing about warm dark matter parameters and inflationary perturbation spectra, and the statistical significance of weak lensing signals across underdense regions. What does the black window mean for someone going about an ordinary life, working an ordinary job, raising a family, or living alone or somewhere in between, on a small rocky planet, around an ordinary star in one corner of one filament in one supercluster of one extraordinarily complicated cosmos? It means, perhaps, this. It means that the universe you live in is more remarkable than you have been told. The smooth, simple cosmos of the standard textbook is a useful approximation, but it is not the full picture. The full picture has hidden layers. It has dark filaments threading through apparently empty space. It has dwarf galaxies you cannot see from your backyard, or even from the best ground-based telescopes. It has, possibly, signatures of pre-inflationary physics encoded in the orientations of structures that span hundreds of millions of light-years. It has the first stars, the first black holes, the first chemistry of life, all preserved in the light of distant galaxies that has been traveling towards you for nearly the entire age of the universe and is finally arriving in this generation in detectors we have built precisely to receive it. You live, in other words, in an extraordinary moment. The moment when the human species, having spent most of its history unaware of any of this, has finally developed the tools to see it. The moment when the dark regions of the skies stopped being dark and started being red. The moment when we discovered, in the most concrete possible way, that the universe was hiding things from us not maliciously but simply because the light from those things was too faint and the right instruments had not yet been built. The instruments have now been built. The light has been received. The reading is underway. And the reading is showing us a cosmos far more elaborate, far more layered, far more strange than any picture humanity had previously been able to construct. This is, in its way, an invitation. It is an invitation to wonder. It is an invitation to look up at the night sky differently. To know that the dark patches between the stars are not gaps in the universe, but windows into it. To know that the light arriving from those patches has traveled, in some cases, for over 13 billion years to reach you. To know that the structures encoded in that light are stranger and richer than any story you have been told about them. To know that you live in a moment when the species you belong to is, slowly, carefully, against considerable difficulty, learning how to read those structures and beginning to understand what they say. We do not understand them fully yet. We are not going to understand them fully for a long time. The Black Window is one chapter in a much longer book that is still being written. The chapter is not even finished. The team is still analyzing the data. New findings will emerge over the coming year. The conclusions we have walked through tonight will be refined, extended, complicated, and in some cases, replaced. The science is alive, ongoing, contested, productive. The story is real, and it is happening now. But the basic shape of what we have learned is, at this point, clear enough to share. The darkness is full, the voids are not empty, the standard model is incomplete. The universe is layered in ways we did not expect. The James Webb Space Telescope has begun to show us those layers, and what it has shown us in one single field of view, in one constellation, in one part of one cosmic web of one universe, is enough to keep us humble for a generation. It is also enough to remind us of something that the references at the start of this script have circled back to again and again. The universe is mostly indifferent to us. It does not care whether we look. It does not care whether we understand. It has been doing what it does for 13.8 billion years, without any consideration of the observers that have lately appeared on its periphery. And yet, despite that indifference, when we do look, when we point our telescopes patiently at the darkest patches of sky and let them collect photons for week after week, the universe responds. Not because it wants to, because it has to, because the light is there, because the structure is there, because the information is encoded in the photons, whether anyone reads it or not, and we have learned how to read. This is, in some sense, the deepest finding of the black window, not any specific anomaly, not any specific candidate object. The deeper finding is that the universe, when carefully interrogated by a sufficiently powerful instrument in a sufficiently empty patch of sky, will tell you things you did not know to ask. The universe is, in this sense, generous. It is not generous with reassurance. It is not generous with comfort. It is not generous with simple stories. But it is generous with information. It hides nothing forever. It hides things only until the right instrument is built, and then it gives them up, gradually, layer by layer, to whoever has the patience and the discipline to receive them. We are receiving them now. The data is on the servers. The papers are in the literature. The conclusions, tentative and contested as they are entering the conversation. The black window is no longer hidden. It is part of the public record of human knowledge. And what we do with that knowledge, how we extend it, how we deepen it, how we incorporate it into our broader understanding of who we are and where we are, is up to us. The universe has done its part. It has shown us the data. The rest is our responsibility. For the team that produced the observation, the responsibility is to keep working, to keep refining the analysis, to keep planning the next campaign, to keep collaborating with theorists who are trying to make sense of what the data shows. For the broader cosmological community, the responsibility is to take the findings seriously, to neither dismiss them as artifacts nor embrace them uncritically as revolutions, but to engage with them carefully and honestly. For the rest of us, the responsibility is perhaps just to pay attention, to know that this work is happening, to know that the universe is more interesting than the standard textbook picture, and that the people who are revealing that complexity are doing so through enormous patience and care, with instruments that took decades to design and build, on timescales that span generations. The next chapter of this story is going to come slowly. Cosmology is not a fast-moving field. Major results take years to emerge, more years to confirm, more years to interpret. The black window observations were made in late 2024. The first major papers came out in 2025 and early 2026. The follow-up observations will run through 2027 and 2028. The theoretical frameworks that may eventually replace lambda CDM will probably not be fully articulated until the 2030s. The understanding we are developing now is being built on a timescale that no individual researcher will fully live through. The senior cosmologists who began the journey will not live to see the resolution. The graduate students who will eventually resolve it have not yet entered the field. The work is generational, but the work is real. It is happening. It is moving forward. And the black window, the 167-hour exposure of an empty patch of sky in the constellation Sextans, will be remembered as one of the milestones in the journey. The moment when the darkness, finally, gave up some of its secrets. The moment when we learned that the simplest stories about the cosmos were not the right stories. The moment when the universe, after waiting patiently for a long time, was finally read in enough detail to begin telling us what it actually is. What it actually is, as best we can currently tell, is layered. It is dark and bright in alternating sheets and threads. It is full of structures that emit light, and full of structures that do not. It is shaped by forces that we have begun to map, and by forces that we have not yet learned to detect directly. It contains stars, and galaxies and clusters, and voids. And within the voids, it contains dark filaments, and dwarf galaxies, and unexpected black holes, and possibly the missing baryons we have been searching for. It contains, somewhere in its earliest moments, the imprint of physics that operates beyond the standard model, physics that we are now beginning to glimpse in the alignment patterns in the bright early galaxies and the dim spectral signatures that should not exist according to the standard expectations. It contains, in short, more than we knew. more than we expected, more than the simplest pictures had prepared us for, and it is, in containing more wonderful, not less. The discovery that the universe is more complicated than we thought is not a discovery that diminishes anything, it enlarges everything. It gives us more to study, more to understand, more to be amazed by. The cosmos that the black window is revealing is not a smaller cosmos than the one we thought we lived in. It is a vastly larger one, a vastly stranger one, a vastly more interesting one, and we are inside it. Conscious, curious, capable of building telescopes and pointing them at the darkness and reading what the darkness contains. This is, on any honest accounting, an extraordinary situation. We did not have to exist. The universe did not have to produce us. The dark patches of sky did not have to contain anything worth reading. But the universe did produce us, and the dark patches of sky do contain extraordinary things, and we have, against considerable odds, developed the instruments to see them. The instruments are not done. Webb is still in its first major observational campaign. The next generation of telescopes is being built right now. The data archive is growing. The papers are accumulating. The analyses are deepening. We are in the middle of an unprecedented expansion of human knowledge about the cosmos, and the black window is one of its most striking recent moments. There will be more moments. There will be more observations, more anomalies, more reframings, more careful, patient construction of a richer and stranger picture of the universe than any human has previously held in their mind. You are alive in the era when this is happening. You are alive in the era when the dark patches of sky are being read for the first time, when the standard model of cosmology is being challenged seriously and openly, when the next paradigm is starting slowly and tentatively to emerge. You are alive at the moment when the universe is, more than ever before, in active conversation with the species that finally figured out how to listen. That is a remarkable moment to be alive in. It is also, of course, a moment that will not last forever. The universe will keep doing what it does, and the conversation we are having with it now will, in time, become part of the long history of how our species came to understand its situation. Future generations will look back at this period the way we look back at the early days of telescopic astronomy, with a mixture of admiration for what was accomplished and quiet awareness of how much was still unknown. They will know things we do not yet know. They will solve puzzles we are currently struggling with. They will look at the black window data and see things in it that we missed, because their tools and their theories will be sharper than ours. And they will, in their turn, point their own instruments at their own dark patches of sky and find their own surprises. The work goes on. The universe keeps turning. The light keeps arriving. And the species that learned, in this strange and brilliant century, how to receive that light, keeps reading. We have not been alone in our wondering. Somewhere in the field of the black window, in the light that has been traveling toward us for billions of years, encoded in the spectra of distant galaxies, there are almost certainly other observers who have asked their own versions of the same questions we have been asking. We will probably never reach them. We will probably never know their names or hear their thoughts or share with them what we have found. But we share with them something more basic. We share the experience of being inside this cosmos. We share the experience of looking up at the dark. We share the experience of being surprised, in slow motion, by everything the dark turns out to contain. That shared experience, even unspoken across distances we will never cross, is its own kind of company. It is the company of every observer in the universe who has done what we have done, pointed an instrument at the night, waited patiently, and let the universe answer. The answers vary. The questions are the same. The black window is, in this sense, not just a piece of data, it is a moment in a much larger conversation. A conversation that has been going on, in various forms, on countless worlds, for as long as there has been anything in the cosmos capable of looking up and wondering. We have just contributed one new chapter to that conversation. Webb has read out one new page of what the universe is telling us. The page is full of strangeness. The page is full of structure. The page is full of meaning, even if we do not yet know how to interpret all of it. The page is in our hands. The reading continues. If you enjoyed this journey into the darkest region of space, please leave a like and subscribe to Hidden Beyond Stars. Tell us in the comments what part of the black window observation surprised you the most. Tell us what you would want a telescope to look at next. Tell us what dark patch of the sky you suspect is hiding something we have not yet found. And tell us what you think the universe might be trying to say, when it whispers from its emptiest places with such patience, waiting for us to learn how to listen. Thank you for spending this time with us. The dark is full. The light keeps arriving. We will see you in the next investigation.